that's
that's the latest here. Somewhere.
That's the recording now. You have to use that to record. Am I going too fast?
oh, here we go.
No, it's way over.
Yeah, that's okay, great.
So that's the projector. That's why. This could be some kind of conference.
I don't know. Yuri, you don't seem to be able to get rid of the picture. It's only like this much, so maybe it's okay.
Maybe let me think whether it's going to be better here or in that corner. Maybe the other corner.
Up above
Well, actually, yeah. Let's maybe the lower right just because that's one. Okay, let's.
Alright. We have microphone for the recording.
Oh, so it's just recording?
And then
Okay, so today's colloquium speaker, Yuri Gershtein of Rutgers University, is an experimental high-energy particle physicist. Yuri did most of his education in Moscow, starting from Moscow Tech, 1992, then went to graduate school at ITEP, also in Moscow, where he graduated in 1996, and continued on as a staff scientist there for a while before becoming a postdoc in the land of freedom at the time. In the U.S., was a postdoc around for a while before getting a position at Florida State in 2005, you told me, right? Yeah. And then he came to Rutgers in 2008, where I overlapped with him for a year before coming down here, but he's been there ever since. All that time working on LHC, or there was CDF in the middle, but he's been working on colliders all that time. And so he's going to tell us today about the Higgs and the discovery, which story we haven't gotten in full here, I think, in a colloquium, so it'd be good to hear about. Great.
So thanks much for the invitation. It's supposed to be a little more colorful, so the red turns out as green. So we'll see how well some of the animations would look.
What color is the Higgs?
It's color neutral. It's a little offset. Well, I guess our eyes will accommodate as we go along. I'll talk a little bit about what is the Higgs, and then since Doug told me that you guys never really had the full story on how it was discovered, I'll do a little bit of the, now history of what happened, how it was looked for, what is the LHC and its detectors, how we found it, And more importantly, what does it mean, right? And where do we go from here? And what the questions new and old the Higgs discovery poses. Right? So, ever since I entered the field, right, in 1992, we were always talking about Higgs as the missing piece, right? So, in the 90s, that was the standard model. You know, that's the general APS DPF propaganda plot with the quarks and leptons and the force carriers, and there is no Higgs, right? So they found it in the poster circa 2000, so now that's that. This decade, the picture looks like this, right? So we have, this is really terrible color-wise. So these are the quarks, these are the leptons, these are the forces, this is the Higgs, and then if you see there's this big blob of something that reads Higgs field. So it's a little weird that the particle and the field are denoted separately. So let's talk about that. So a little bit about the fields. So standard model is a gauge quantum field theory, right? And it might be a theoretical bias, but we'd like to keep it this way. This is the only way we know how to describe the world. So field is a quantity associated with every point of space and time, right? So if you can plot the temperature in this room and every point of the room, that would be a field. Maybe not very interesting, but it would be a field. In the E&M, we'll get through that. In the E&M, you have vector fields, right? So each point has an electric and magnetic field vectors that obey the Maxwell equation, right? And then when you go to the quantum, the fields quantize, right? So now they would have the fields would have ripples on them, waves. Those are the particles that we perceive, right? The energy quantizes, right? They come in discrete packages, E equal h nu for a photon. And you can go into the second quantization and describe the system, but basically making a list of how many of these quantum packages are. And you're done. Right? So field is the fundamental object, and the particles are sort of the consequence of that. Right? So theorists would really be interested in the field. Right? I'm an experimentalist. I'm interested in the particles, because studying the particle is really the main source of information about the field. So, why is Higgs field so weird? Higgs field is really weird, right? So, first of all, it's a scalar field. It's a spin zero particle. We've never dealt with those before, and I'll come back with why spin zero is so peculiar. Part of it is by design, because then you can make the Higgs field non-zero everywhere in space, even though there are no particles. Right? So, electron is a field. If there are no electrons in a particular volume, the electron field there is about zero. Right? It's not true for the Higgs. Right? There can be no Higgses, and yet the volume will be filled with the Higgs field. Right? So,
can you repeat that? What exactly do you mean?
It's the value of your field if there are no, so electron is a field, right? If there are no actual electrons, if there are no ripples in that field, the mean, the expectation value of that field in the volume with no electrons is approximately zero. Well, approximately. With the Higgs, it's not true, right? There can be no Higgs particles in a particular volume, but there will be a huge amount of field.
Is it the same as photons and electrostatic field, or?
No. When you have electrostatic fields, you have photons flying all over the place. Your field is very much non-zero.
For static field?
Yeah. So this is really an exceptional thing, and it's exceptional by design, right? Well, because you can ask, why would you invent such a thing? And you need that such thing to make sense of why elementary particles are massive, right? And it's not clear, how that one follows from the other. So just as a little bit of a sideways of how we get to the need of the Higgs field. Your classical undergraduate E&M, you have 4 Maxwell equations. You can derive conservation of electrical charge from that, right? It's encoded in those 4 equations. A way to look at E&M, right? If you remember, also there's an alternative way to look at this, right? You can introduce scalar and vector potentials. They will be really neat objects. Well, first of all, they will form a 4-vector. And the second of all, it kind of comes as a curiosity, and the thing in the classical E&M, some things are easier to calculate in one gauge, some are easier to calculate in the other gauge. They're not unique, right? So you could do what's called the gauge transformation to them, and nothing will change in the system, right? Nothing. Right? Well, when you go to quantum, it actually turns out that you can treat this as a special case of symmetry. And symmetries are nice things, right? So if you have a symmetry of a particular kind, you should have a corresponding conservation law that comes with it. And it turns out if you do quantum electrodynamics, the electric charge conservation, you can start with something that has gauge invariance, and you get the conservation of charge out of that. Was it an amazing feature, and ever since that was realized, basically every theory that people came up with, if you need conserved charges, you build something with a gauge symmetry. However, the big limitation here is that the gauge symmetry is only true if the particle has 0 mass, right? So in your Lagrangian for the quantum field, whatever is the interactions, but the term which is proportional to the square of the field, right, is that mass, right? And obviously, if you square that gauge transformation, you will not get that symmetry back, right? So.
What is gauge symmetry? It's just the symmetry that's derived.
Yeah, it's basically the fact that I can. The classical analog is that I can adjust the gauge, right? And here, when I plug it into a linear Maxwell equations, everything works very nicely and things cancel, right? But if I try to take the field square, it stops working.
Okay.
So, if you want your W's and Z's to be massive, you're out of luck. Right? So the solution to this impasse was found sometime in 1964. So basically, way to introduce gauge symmetry into theories with massive particles, based on some condensed solid state physics idea of Philip Anderson, and basically several people, Englert and Grout, Higgs, and Grolnick, Hagen, and Kibble, came up pretty much at the same time with this mechanism, which is called the Higgs mechanism now. Right? So remember I was saying that Higgs is something that fills the space no matter whether or not there are particles. Well, if you remember your special relativity, the mass in special relativity is rest energy, right? So you fill your space with something, you make everything interact with it. Well, the potential energy of that interaction is your mass. If it sounds like a trick, it is. Okay? That's basically what the Higgs is, right? That's you found a way to create this field that everything interacts. Interestingly enough, you can actually have a not just static but a dynamic analogy with this as well, right? So if you have a tub filled with something, a photon which doesn't interact with it goes through, and the W, which is very interacts with it very much, scatters around, right? So that's not dissimilar to what Sommerfeld mass of electron in the crystal is, right? The mass of the free electron in the crystal can be way larger than the mass of the electron itself. So that's the big idea. That's what the Higgs is, right? It's a trick, right? You need a scalar field like Higgs, and you need spontaneous symmetry breaking, right? So if you want to make a massive photon, you devise your field like this, so a complex scalar, and that looks very symmetric, right? So this is your zero field point. It's nice and symmetric, and gauge symmetry is preserved because gauge symmetry in this case is just rotation, like this. But this isn't your vacuum. This isn't your stable state. This is your stable state where the symmetry is broken. So for the standard model where you have to give mass not to a photon but for the W plus, W minus, and Z, you have to have complex scale, complex doublet, so 4 degrees of freedom. You give mass to W and Z, and there is 1 degree of freedom left, which is the Higgs. So that's it, right? So Higgs is a particle corresponding to the fluctuation of the Higgs field. That's what gives the mass to everything. That's the only way we know how to give mass to the particles in the standard model. And it is indeed a trick, right? It's not unlike Ginzburg-Landau potential, right? I mean, in fact, that Mexican hat potential even looks like Ginzburg-Landau potential. Right? So that's why we love it. The slides are really much more colorful on my display. So, how to look for it? Well, you can go to Scotland, where you find a person who mastered to smile exactly in the way that the real Higgs smiles, which you buy on the particlezoo.com, for $9.75. People really started talking about finding Higgs as a main priority for the field in the early 80s, right? So that's more than 3.5 decades ago. The only unknown parameter for the Higgs is the mass of the actual boson. Everything else, once you fix that, all the properties are fixed. Higgs, remember, Higgs gives everything mass by interacting with them, right? So if you have Higgs, it will decay preferentially into heavy particles because it couples to them more. And it's much more efficient to create Higgs by colliding heavy particles because it couples to them more. Right, so these are from really old papers when people hope that the Higgs mass is fraction of the GeV, and you see how this goes, right? So if it's below neon threshold, it goes 100% into EE, and then if the neon channels opens up, it goes entirely to mu, and when the kaons showed up, the strange quarks, it goes totally to the strange quarks, and then once B is available, it goes mostly to the B quarks. And then once W's and Z's are available, it goes mostly to the doubles, right? And somewhere here, it will go totally to the top quark. Well, mostly to the top quarks. Right?
So Higgs boson is providing mass to other particles, right? How about this kind of mass? Like, there must be some other fundamental.
That's a fundamental parameter of the theory. Right? I mean, you write that potential. This is your potential, right? I mean, right? The problem, right, with giving mass is that if without the Higgs, if I go and write by hand a mass term for my W in my Lagrangian, I will find that my theory has lost gauge invariance and there is no conserved charges anymore. Right? So here you find a way to introduce a particle that somehow solves that, right? With this neat kind of trick.
Why did you say that fermions had to be massless too? Right? Sorry, I just. So bosons, gauge bosons, I understand, but why do fermions have to be massless? According to the argument.
I think you still run into problems with the why fermions have to be massless.
Well, they don't. I mean, Dirac equation coupled to electromagnetism is perfectly gauge invariant, right? Or gauge covariant, if you like.
No, but if you want, I think if you want W's coupling to them, I think you still run into trouble. I'm blanking right now for what is happening, but it's.
Maybe.
So, since the 80s, people have been looking, right? There were a lot of false alarms. So the first one that I remember was at the crystal ball experiment, right? That was producing epsilon 1s meson at rest in the plus or minus collision, right? So if the Higgs is below is kinematically allowed, this is the perfect decay through the photon and the Higgs. This guy is at rest, so you should see a monochromatic photon. And that actually looks like a very convincing peak that they managed to produce. Argus, that was another experiment on the same storage ring, quickly disproved it, and then it went away. And I think the crystal ball moved after that to this country. So then lab started, and this is, so it doesn't show blue as well, light blue. This was supposed to be a little error band on this. So it actually, there is a caveat to this statement that Higgs is the only free parameter in the theory. Free parameter it is, but particles like W and top feel the Higgs because of the quantum fluctuations where it can split and emit the Higgs and absorb the Higgs. That changes the mass of the particle. So you can look at the mass of the W and the mass of the Z and figure out what is the probable value of the Higgs. And that was sometime in the late 90s or something, we settled on the thing that, well, it's likely somewhere around 100 GeV plus minus, a few tenths of the GeV, right? And then there was a limit from left one around 40 GeV. People in this country spent about $2 billion building super collider. That didn't go anywhere. It was a false alarm. And then the most recent ones was from Lab 2, right? That was supposed to be a Higgs factory. So you collide electrons. You don't produce Higgs exactly from the colliding electrons because the electron mass is too low. Instead, you go through a virtual particle, meaning that you get some suppression of it. But because it's so much heavier than electron, this still wins in terms of frequency of events, right? So you produce Z, and Z emits the Higgs. That was a very convincing plot for a while, right? So you go and look at the masses of your candidates, and the yellow is the background, and red is the signal. And as you go from loose to medium to tight, you see that the yellow decreases and the red goes up, and that was very exciting. Unfortunately, lab basically ran out the clock and time they couldn't really go to the higher energy because if you make electrons go in a circle, electrons radiate, synchrotron radiation. And because the electron mass is so small, they radiate a lot, and that's a very strong function of the energy. So there is given the size of the ring, they basically ran out of the available power to accelerate, keep electron energy intact. That was what we call 3 sigma signal, right? That was actually pretty exciting. A lot of people believe that they discovered the Higgs. Which brings us to, well, it's the same tunnel as the lab, right? So they actually had to, as the lab physicists were beating themselves on the chest and saying that they just almost discovered the Higgs, their magnets have been ripped out and another accelerator was put in that collides the protons. It's a pretty big ring, it's 27 kilometers. So to size, this is the landing strip of Geneva Airport. There are 2 general purpose detectors, Atlas and CMS, so I work on this guy. People know about the energy of the LHC. This is really the most energetic collider that was ever built. It's 7.5 tera-electron volt per beam. The number that I really love about this is the other axis here, which is the stored beam energy, right? You have, in the LHC, you have probably a nanomole of protons, a nanomole of hydrogen in the beam, right? So it's very few protons, 10 to the 14th, something like that. Yet you accelerate them so close to the speed of light that the energy that nanomole has is 400 megajoules, right? So if you're a little rusty with what megajoule is, it's enough to heat up a ton of water from 0 to 100 C, or basically 100 kilos of TNT, or in theme with our location, about 25 pounds of
That's pretty powerful.
It's good chocolate, man. So, as I said, we accelerate protons. They're stable, so we can take time accelerating them. They're heavy, so they don't radiate a lot. The problem is they're not elementary particles. So you think you're colliding billiard balls, but you're colliding bags of jelly beans, right? So if you look at the energy of each individual collision, right? So, well, sure, every once in a while we get like this, a collision like this with a large energy, where proton does look like 3 quarks, right? But most often, you get something like this, where if you look at the constituents of the protons that carry only a small fraction of its energy, it's a bag of jelly beans, right? So what mostly happens is something like this. You have 2 tiny, little particles colliding and giving you 2 what we call jets of particles, right? That's completely uninteresting, not calculable, and it's like sand, it gets everywhere. Also, because most of the collisions are like this, if you want a reasonable number of guys like this, you have to go to a regime where every time the beams cross each other, you want to have several interactions. So that for each this guy, you have like 20 of those. And, by the end of the LHC, we'll have 200, in the same event, we'll have 200 collisions like this, and one may be interesting.
What's the event down there at the bottom? You're thinking of quarks?
No, it's 2 gluons. Actually, if you look at the small, the number density
I understand the jelly beans. What's the other limit?
What is the proton, what are you thinking of the protons to look like?
Well, if you look at the protons, the constituent of the protons that carry large fraction of its energy, then you have three quarks,
Okay.
right? So UUD,
Quark.
as it's clearly seen in that. So, how do you do physics like this? So you build the accelerator, you manage to collide beams, you want to observe what's going on. It's been a long time since Chadwick and Rutherford did their experiments. The detectors got a lot more sophisticated. The idea is still the same. You have source of radiation. You discriminate between sources of radiation by seeing how far each radiation penetrates. Well, you also have put things in the magnetic field so that you can tell the charge. But instead of walking you through, so some particles like muons go all the way through, some particles get absorbed early, some particles get absorbed somewhere in the middle. Instead of going through the... what happened? Oh, now I'm going to be in trouble because I need... can you move that window somewhere? Because that's where I need to press play. Okay. No. No. Oh, come on. Here we go. So the proton bunch starts, goes through the booster, goes through the PS, that's where all the neutrinos experiments of the 70s were done, and then goes to the SPS where the W's and Z's were discovered, and then you finally goes to the accelerator, the LEP tunnel, which is now the LHC tunnel, which is crossing some state lines as you go along, and it looks a little better when you have red. So you have proton on this side, you have another proton on the other side, and they collide, and then all the kind of stuff comes out. And here you see, it's really hard without the color. So there are darkish green color, which corresponds to the particles that get absorbed in the earlier detectors, and then no, this is truly terrible. And then in the other shade of green, which is the hadronic colorimeter, when things are reconstructed, and then these little squares that you see are the detectors on the very outside of the detector, which detect particles that traverse the entire thing. And that's the most common event. Like I had a diagram for a couple of slides back. You have a jet of particles, you see some particle tracks pointing this way, and some sort of irregular object, irregular kind of shape energy depositions. Right. So the detectors themselves are a marvel of engineering and ingenuity and just this mind-boggling scale, right? So we have enough brass in our hadronic colorimeter to build a couple of colossus of Rhodos and more iron in our return yoke to build a couple of Eiffel Towers. And that was the time it was built was a hopeful time. It was the 90s, right? So that colorimeter was used Navy shells back somewhere under St. Petersburg. It's a work of great many people. So that's, I guess, I think somewhere over there. And it's paid by great many people. If you like, this is the triumph of the taxpayer-subsidized science. Right? So if you pay taxes in any of the colored places on this map, you actually paid for the Higgs discovery.
What do the colors mean?
Well, if you remove the red, they don't mean much. But some of them, so the blue means full member state, and then different shades mean the different type of state agreements with how CERN is
I
funded.
was hoping it would be dollars per capita.
No, it's not dollars per capita, it's a little different. But the statement, however, is that if you live in the country which is colored by any color than white, which is supposed to be light gray, you actually contributed to the Higgs discovery. Okay, so how does Higgs decay? We already said that it mostly decays to the heaviest particles. So you'd think that you want to go with something like BB bar, right? So Higgs decays to 2 B quarks. Bad idea. B quarks form these jets. You can't measure their energy. Well, you drown in background. Right? So you really have to go all the way down to something like 2 photon decays to get a good mass measurement and to get good signal to background. Right? So even the WW, which is in this nice pinkish red curve shown here, you think it's kind of high branching, but then once you see how W decays, it decays either to jets, which are hard to measure, or it decays into leptons which involve neutrinos, so some of the energy escapes, and again, you don't have clean mass. So the same story with ZZ, which is also kind of somewhere here, because mostly Z doesn't decay into particles that give you nice clean mass peaks. So if you convolute, so this is just the probability of the Higgs to decay, so this is sort of where you convolute everything together, production cross-section and decay branching and everything, and you see that, right? So this is about a femtobarn of data. To give you a sense of scale, when Higgs was discovered, we had 10 femtobarns, something like that, right? So you're really relying either on this red curve here, which is Z to 4 leptons, or this curve here, which is Higgs to gamma again, right? So these guys are more numerous, but the background is high. These are what was called the gold-plated channel, but you're really talking about a handful of events.
Are those all predicted theoretically?
Yes, right. So that's exactly that's the beauty of this, right? So this is really just one parameter. Once you fix the mass, there is absolutely no freedom in the standard model. So let me first show you the gold-plated channel. We have 2 decays like this, and right, so you have 2 collisions, and now you see the event look completely different. So you have these very regular, very nice, narrow deposits of energy here. That's from VZ that decays into the pair of electrons. And then you have these penetrating particles that are crossing the outer detectors, which are the muons. Right? So those are very rare events. And, your analysis is fairly straightforward in principle, right? You select all the events that looks like this, reconstruct the energies of the particles, and construct invariant mass, and make a plot. So in July 2012, this is how this plot looked. And you see there is a little bit of an excess here. Not terribly significant. Well, exactly, we know exactly how significant it is, but about 3 sigma significant. So kind of like what the lab saw at 115 GeV. So this is very hopeful, but really nothing to write home about. So the second channel that I said was the other promising one is the Higgs decay into two photons, right? So this is, again, you see the really nice and narrow depositions with no tracks pointing to it, so there are photons and not electrons. And you look at the events like this and plot invariant mass, right? And this is what we saw in 2012. So you have a whole lot of events here, and most of them come from just quarks and colliding with antiquarks, annihilating into two photons. That's your standard process. And then you see that at around 125 GeV, you have an excess, right? So you have two gluons colliding, forming a Higgs that decays into two photons. Right? So that looks straightforward enough until you look at the axis and see that these are actually weighted events, right? So in fact, if you don't weight the events, your peak, well, it's kind of still there, but it pretty much completely disappears. Right? So the whole magic of doing the Higgs to gamma-gamma analysis sits obviously in that weighting of the events.
Weight by what?
Good question. Right? So why do you need those weights? Well, I mean, that event that I showed you with two nice narrow deposition, that's what we call a typical event, right? Which of course means that it's not typical at all. There are so many conflicting goals when you build the detector like CMS. Like, for example, you want to measure trajectory of charged particles with large precision. It means that you need a lot of material in the tracker and a large magnetic field. That's exactly what you don't need if you're trying to do physics with photons, because in the end, you end up with the amount of material which varies from half to 2 radiation lengths, which means that basically almost half of all the photons that go through the detector start showering, right? They convert into 2 photons and start pair producing, right? So that's the distribution of the material, right? If you can actually, we spend a lot of time trying to nail this exactly from the data, but the effect of this is here, right? You generate 2 you see this is green. You see, so you generate 2 photons back to back, and you expect nothing in the tracker and 2 very narrow signals here in the colorimeter, and you see something like this, right? So this is obviously some of the parts of the shower that didn't even make it to the colorimeter because magnetic field curled them away. And then instead of nice, nice shape, nice little tight signal, you get something like this because the magnetic field spreads this, stretches the shower along. So you really have to go and collect things from a large area, add this all together, and once you start adding energy over a large area, you run into another problem, right? You remember I said that you have these extra 20 events bubbling around, right? Well, these events are not particularly energetic, but they contribute energy, right? And so you start absorbing a lot of spurious energy into your photon as well, right? So there was a lot of work that went into trying to understand how to separate those particles from the photon showers from the pileup events, how to reconstruct the energy of this, right? So you actually see that this is the area over which you collect energy for the photon. And you see there is actually, it turns out that there's a very nice pattern in it, right? So this is if you have just photons without the pileup, and this is if you have photons with pileup, right? You see that, there's the same, it really is terrible projector. So there is the same sort of mustache-like thing, but then there is also a whole lot of scatter that you really just need to remove. Right? Even worse, right? When you get the photon that didn't convert, you get a very good energy measurement. When the photon converts, you have a really crappy energy measurement. If you had a perfect photon, and then you also got something from pileup, it now looks like a converted photon to you. So you try to correct its energy to while you shouldn't, right? So there's in the end, we made a pretty big boosted decision tree that actually regressed, given all the information that we could from the cluster to the photon energy. So this was our way to get the energy resolution for the photon, to improve the energy resolution, right? So it's basically, I mean, if you have the only observable that you measure, and this is your function, right? It's trivial to one dimension to make the calibration curve, right? If you have 10 different variables, that becomes, what we call just the regression, but now is fashionable to call deep learning in the actual analysis, right? So you go, and this is your first regression, right? You go and you try to get as best measurement for the photon as possible. The next thing is that although we improve, in many cases we manage to put the Humpty Dumpty back together again. So once the photon converts, we're able to actually recover a lot of its energy. It's never going to be as good as new, right? It's still going to be a poorer resolution than your gold-plated ones. So what you also want to do, if you can, you want to look at your photon on a photon by photon basis and tell you, like this one was measured well, and this one wasn't measured very well, and this is kind of in between. Right? So in the first analyses, back in 2011, we basically said, well, if there is if it's a one peak in the cluster, it's good. If it's not one peak in the cluster, and that's like the other ones, then it's bad. Right? So we could be smarter with this, right? So we basically made the second regression that now wasn't going to guess what the energy was, but was going to get the resolution. And you basically regress. It turns out that you need to regress to the absolute value of reconstructed energy minus true energy divided by the true energy. So you have this sort of ugly half-Gauss thing, if you think about, Gaussian of width 1, right? And you would regress to this mean, which will be proportional to your sigma, right? It will be with a coefficient of 125. So we trained this regression, and then, well, in Monte Carlo, in our simulation, we can use that, look at the photon resolution in bins of our predicted resolution. And indeed, the ones that were supposed to be good are good, and the ones that are supposed to be terrible are terrible. And you go and you fit them with a Gaussian, and you can actually plot one versus the other, right? So this is the actual, this is the predicted, and this isn't a fit. This is my coefficient of what it's supposed to be. And then, of course, you can check it with the data in many ways. You have Z2EE, which can tell you a lot about how to do things. But the second step is really what made the analysis so powerful, right? Because now you don't have to lump together your best Higgs candidates with your worst Higgs candidates. You can go and separate them into different baskets. And that was the 11 baskets for the July 2012 analysis. And there are yellow and green bands on these plots. But you can see, right, that the signal to background in this category is completely different from the signal to background in that category. Right? So now these 11 plots are the plots that actually goes into calculation significance. The plot that I showed you before is really just a PR plot, right? You either just add them all together, or you add them with the weights corresponding to the signal to background that you see. Right? So it's still a fair plot to make, and it shows you the power of that you get from your improvements. But this is the actual data that you derive your significance from. And in 2012, it was, trust me, it's 4 sigma down there. So together with the 3 sigma from the Z to 4 leptons, that was enough to claim the discovery. And that was surprisingly big event with a lot of, and I think a lot of people were surprised by how much people cared. So, we didn't stop there, right? So by the time we finished the run, we basically doubled the data set that we had, and now you see it's, at some point we stopped counting sigmas, right? So this is actually fresh off the press from run 2. Again, you see this is our weighted events improved, this is unweighted events, right? Well, by now we have significant signal even if we don't weight, but you still get quite a nicer and narrower signal if you go through the trouble of the categorization, right? So, and the Z to E is also now, Z to 4 leptons is also now fully established at, well, you don't see how many sigmas it is, but 5 sigma is somewhere here. So now you can do precision measurements with this. We have so many Higgses that we actually can say more than, oh, we have discovered a new particle, right? We can, remember we needed it to give mass to things, so we can measure the coupling of Higgs to different particles, right? So from the tau all the way to the top quark in mass, we can do the measurements. So the black line is standard model prediction. So the vertical lines are errors. It looks like it's coupled to mass, right? You can go and combine different channels and see how far you are, say, in couplings compared to standard model in couplings to just fermions or coupling to just W on Z. And you see we're actually pretty close, and it couples to mass. So, we discovered the Higgs. This is, in this decade, how we prefer to talk about the Higgs, about the standard model. What's left to be done? I really enjoy this quote from Michelson. It's a famous one that he gave in some of the commencement addresses in some university somewhere. That everything has been discovered. There's actually, you can look it up. There is actually, a very passionate defense of what we now would call intensity frontier, right? It has cites discovery of argon and other things. What I find amazing about this quote is not that it's one of those which are patently wrong. It's that he made this statement 7 years after he made his experiment with more. Right? So you can sit for this long on something that completely appended physics and not realize it. And the second delicious thing about this is that, this is Peter Higgs getting the Nobel Prize for discovery of what appears to be a fundamental spin zero particles of a quantum scalar field with not zero vacuum expectation value, which if I wanted to come up with the definition of ether that would be Lorentz invariant, that would be it. Right? We made this stub, we filled everything with a Higgs field, it is our new ether. Right? So what does it mean? Why do we have this vat of ether in the universe? Right? So the standard model just says, that mu square is less than 0. That's what it is, right? And I find it very deeply unsatisfying, right? I find it's the same as if to say that Ginzburg-Landau theory describes superconductivity, period. I mean, you can say that, and it does describe a whole lot of superconductivity, right? But you'd be missing completely all the microscopic explanation of what actually, there actually is a new force, there is a new particle, it's called the phonon, and it's these interactions that make this potential. So, if you want more than phenomenological trick to explain why there is such thing as spontaneous symmetry breaking and why we need Higgs in the way it is used in the standard model, you need a new force and therefore new particles, right? So, could be one, could be many, who knows? So this is where we are. Don't forget, the LHC, it seemed like a thing for a while. And I just remembered this morning that the first plot I made with a CMS label on it was in 1994. So it's been a while. But we've been running on our nominal energy and nominal luminosity for a year? Yeah, right? So about a year ago, we finally hit the nominal luminosity with the nominal energy. And we sit in this really peculiar place where the electromagnetic force is unified with the weak force. So, why is it a special place? It seems to be a special place. Higgs mass could have been anywhere. Higgs mass sits here. Right? It actually is a good mystery why the Higgs is so light. Because if we really claim that this is all there is until like grand unification or even the Planck scale, right? The fact that the Higgs has to be a scalar particle has a huge self-destructive feature in it, in that it receives quantum corrections to its mass from fermions and bosons, and each one of them are of the order of the Planck mass. Right? So you sum up the number, several dozens of numbers of the order of 10 to the 19, and somehow you end up with a number that is 10 to the 2. It's hard to believe in coincidences, right? So people, even before Higgs was discovered, well, that was one of the reasons why many people did not believe that the Higgs exists, because of this property of the fundamental scale. Right? People went and attacked this on the very lawyery things, right? This is a true statement, so you can go and dismantle it one by one, right? So it may not be fundamental scalar. Then there are models of composite Higgs and so forth. The Planck mass may not be as high as it is. We say that it's 10 to the 19th GeV because gravity is so weak. Well, it turns out that it doesn't have to be really weak, right? It may be that we live not in the 4-dimensional space, but in more than 4-dimensional space. And then gravity leaks in the other dimensions, and electromagnetism, for example, doesn't. So the gravity just seems to be weak, but it becomes quantum at the energies of about TeV or so. Well, TeV now is excluded, but 10 TeV probably isn't. And finally, there is a conspiracy. Another explanation over this is the conspiracy, that these corrections are actually supposed to cancel, right? And that's what supersymmetry is. Whatever you do to this, you have to have new particles, right? Which is the flip side of the argument that to understand the Higgs potential, you need a new particle. Right? These would be the particles that make that Higgs potential. So this is the game plan, right? So right now we're here in the middle of CERN loves acronyms. I think it stands for Extended Year-End Technical Stop. Right, so we're about to start running again. We're now running at or a little bit above our nominal luminosity. We're going to install a bunch of more upgrades in 2019-20, and then run for a little bit more, and then around this time we'll basically upgrade at least the luminosity of the LHC, and maybe even some of the energy. And even without the energy upgrade, this is how that plot will look like by when we're done, right? You remembered the size of the errors that we had on the other plot that I showed before, and you see there is a muon down there, so we'll actually have enough data to measure Higgs coupling to the second generation particle, which is extremely important. And then a lot of the dark matter and supersymmetry parameter space will be enhanced, will be covered. That can only be covered with such high statistics, because some of these supersymmetric particles are, even though they're light and can be produced, the signals that they leave in the detectors are so puny that you really need very high statistics to eke them out. So this is it, right? I think, so LHC is a discovery machine. We discovered actually more than the Higgs. There were actually a few other things that were less fundamental, but nevertheless very, very cute, both in the particle physics and the heavy ion physics. And yeah, we'll continue running for a long time. We just made this math over lunch. Tevatron ran for 33 years, right? Or something like that. So, we're going to be running into 2030s, and it's going to be fun. It's not going to be any more no-lose theorems. For the Higgs, we had a no-lose theorem because there was this great feature that there was a standard model process of WW production, W pair production, that if you calculate it in the standard model without the Higgs, gives you the probability of the process that is greater than 1, which is bad. So you either discover the Higgs, or you look at the WW production and notice how that probability does not turn into 1, and that tells you something. Right? So with the why Higgs so light and what makes Higgs potential, it's hard to come up with a no-lose theorem like this. But, you know, we've been doing this collider thing for a while, and every jump in energy usually gave us something interesting. So I think I still hopeful that we're in there for a surprise or two.
What's the annual cost of running that machine compared to the capital outlay?
Compared to?
The capital outlay.
How much it costs to build?
Oh, much, much smaller, right? I mean, it's really hard to, actually, the number of, how much LHC cost is surprisingly hard to calculate, because the US counts money one way and the labor the other way. It's order of $10 billion for the entire thing, but there's a factor of 2 uncertainty there. Running it, I think it's in the maybe tens of millions a year. It's not that much.
But that doesn't count the experimenters.
The experiments are actually surprisingly small fraction of the total cost, right? So when I say that to build the accelerator cost order of $10 billion, each experiment cost probably 300 million, right? So
Including the scientists.
including some of the labor of people who built it, yes. Depending on the nationality, it's either not included or not included in the...
Since we're talking about money, how much does it cost to go one order of magnitude up in maximum energy? Is it also
Going a factor of 2
historically?
I don't think it's an order of magnitude in money. It's I don't have hard numbers to tell you. Right?
I've heard that these basically scales. So you multiply by 10 to go 10 times in energy. So does it mean this is the last?
Some fraction of it scale, because if you need a longer tunnel, well, the tunnel costs scale very well. Right? The magnet costs scale very differently, right? I mean, if you like, the big use of the superconductor magnets is something that started the MRI revolution, and it's hard to estimate the cost to society from something like that.
This is if it does scale it good for you, you will run forever because the competitor will never be built. So this is the last thing.
It's unclear what will happen. I mean, it's clear that you really would need something else if nothing else shows up. Well, we'll see. Maybe we're missing something trivial, that new physics is in the data that we have now, and we just haven't looked in the right place. Right? It could be that we'll eke something out in a few years. Right? I mean, in principle, right? I mean, in the grand scheme of things, this is not a big amount of money.
Well, I don't know.
Depends on how grand the scheme is.
As to quote Leon Lederman, who was asked at some point by DOE secretary or somebody who was saying, well, you're spending all this money, and how does it contribute to defense of this country? And it doesn't contribute to defense of this country, it just makes this country worth defending.
So for the Higgs field, is there a way to estimate the energy density of this Higgs field?
Yes, you know how much it is. It's 246. 246 GeV per. Oh God. Everything is unit 1, right? So it's 246. 246 GeV, right? So yeah, there is a certain HC factors that will
much larger than the
Oh yeah.
120 orders of magnitude, right? That's the biggest error of physics.
I wonder, isn't your quark itself a bag of jelly beans?
Quark? No. As far as we know, quark is an elementary point-like particle.
Okay, all right. That's a relief. All the way down, it's jelly beans. You open up a jelly bean, and there's a bag of jelly beans.
It's turtles. When you get to the bottom of it, it's all turtles.
Does it make sense to ask about the units of the Higgs field?
Sure, right? I mean,
what are the units?
Well, GeV, I guess. You have a theorist here who should help me out. The energy density will definitely be in GeV, right? And that's a squared, so square root of GeV. How's that? Oh no, it's m square a square. M square a square. So it's unit. Yeah.
So maybe it doesn't make sense, but your electric field, you would have something that was based on the electric charge, right? Would be an element of figuring out what the field is. And wouldn't you have to know what your force was to know what the field?
Sure.
So what is the force? I mean,
it's the gradient of the potential, right? No, but seriously, right? So if you so in Lagrangian you get m square, a square is your mass term, right? So a therefore I guess is a unitless number, right?
In the electric field,
In the electric,
you have E squared over C, right?
yeah,
And so the units there, it's energy still. The square root of energy would be the units of the field, but then the C converts it into coulombs per meter.
right.
Not coulombs.
Yeah. My mind is sort of split in the SI units that I teach E&M with, and the regular units where C and H is equal to 1.
But the
and,
C is, and so
Yes.
that's the permittivity and
Yes.
permissivity of space, converting that energy into the units you're thinking of
Yeah.
for the field in the electric field case.
Yeah.
In the Higgs field case, we're just saying it's the energy there, or the square root. When you square it, you get energy density.
Can you
And
say,
it's scalar, so it doesn't point in any direction like the electric field does.
So if the field, if you had multiple choice, could be the force rather, we're strong, weak, gravity, electromagnet, or is it some other force?
It's not all the above, yeah.
It's not a force.
It's not a force.
It's not a force.
So you have a field without a force.
So we talk about it being a boson that's different than the other bosonic force carriers in that sense.
Yeah.
It's not really a force carrier.
Right, so its purpose is to have this, have this ether that gives everything mass.
can you talk a little bit more about that process? You've got this space filled with Higgs
Yeah.
stuff, whatever, a field, and now a particle going through there acquires mass. How?
As with all analogies of the quantum, it's a little contrived, right? So I guess the correct question for this, there is this term in Lagrangian, and that's what happens. The most, I think, illuminating analogy, although it's not perfect, is, if you make Higgs interact with everything, you would interact with the particle, then there is some potential energy that is your rest energy of the particle, right? And that becomes your
This is just mass.
So
The mass
Yeah.
of that H boson is just the superfluid density for a superconductor in Weissner's thing.
all right, that's good enough for you. No, we think of mass of an electron coming from coherent collisions of nuclei in a solid, so the mass changes. The
Right.
other possibility is we have a many-body, many electrons.
right. So it's not a perfect analogy. I mean, the actual Higgs mechanism doesn't do the same thing as why the electron mass in the crystal is larger.
Is
Right?
electrons bumping into Higgs particles?
Not particles, no. Higgs field, right? It's
Well, how does it
It's-
interact with the field if there's not a particle?
So the electron field interacts with the Higgs field. How about that?
I don't like it.
well, you don't have to.
I'll work on that.
So I mean, I don't know a good classical analogy of.
Yeah, I always want a classical. I always want Newtonian physics. I'm with Michelson.
Well, if you heard about the prime minister analogy, right? That there is a room of people, and then prime minister wants to cross from one end of the room to another, right? So if the room is empty, she can do that. right? If the room is filled with the diplomats, she has to talk to
This is
any of them.
viscosity. This isn't mass. This gives viscosity.
You're a hard man to please.
So it's like dispersion of quasi-particles in the presence of superfluid condensate, right? You get a gap which comes from the strength of the condensate.
Any other questions? If not, let's.
This
Yeah, I think so. Oh, I need to give back. I need to give back the thing. I almost walked away.